Hello and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Rebecca, lead tutor for biology and chemistry. In today's video, we will explore Lewis dot structures. Let's get started. Let's first understand what Lewis dot structures are. They are simplified representations of elements' valence shells using dots, lines, and element symbols. The dots represent the valence electrons. The number of the main groups in the periodic table are the same as the valence electrons of the elements in the respective group. This, however, does not apply to the transition metals. For example, fluorine, which is in group 7A, has 7 valence electrons. Oxygen, which is in main group 6, has 6 valence electrons, and so on. Valence electrons aren't just drawn anywhere. Imagining a square around an element symbol, there can only be a maximum of 2 dots on each side of the element symbol. Chlorine has 7 valence electrons, and its Lewis structure is drawn this way. When drawing the Lewis structures of compounds and molecules, bonds are illustrated by lines. Each line involves 2 electrons. Single bonds are depicted with 1 line. Double bonds are 2 lines, and triple bonds are 3 lines. The octet rule states that elements lose or gain electrons to have a total of 8 valence electrons and become stable. Elements that tend to attract electrons to fulfill the octet rule have 4 or more valence electrons, and these elements are typically found on the left side of the periodic table from group 4A to 7A. Elements on the second period of the periodic table lack D sublevels and only have S and P sublevels that comprise the octet or the 8 valence electrons. Thus, second period elements such as carbon, nitrogen, oxygen, and fluorine obey the octet rule without any exceptions. Let's take a look at some examples. Carbon has 4 valence electrons, so it must form 4 bonds to have 8 valence electrons to fulfill the octet rule. Oxygen has 6 valence electrons, so it must gain 2 more electrons to fulfill the octet rule. It does this by forming 2 covalent bonds. Fluorine has 7 valence electrons and only needs 1 more electron to have 8 valence electrons. Thus, in a molecule or compound, it is likely to form only 1 bond. Certain elements can have a stable electron configuration while still having less than 8 valence electrons after forming bonds. These elements are said to have incomplete octets. Some common examples of elements with incomplete octets are hydrogen, lithium, beryllium, boron, and aluminum. In a hydrogen molecule, each hydrogen has 2 valence electrons in its shell after sharing a bond with the other hydrogen. Beryllium in beryllium fluoride has 4 valence electrons after bonding with 2 fluorine atoms. Boron trichloride is stable with only 6 valence electrons on boron. Elements that can potentially have more than 8 valence electrons after forming bonds are said to have expanded octets. For elements after aluminum, a D sublevel exists that can accommodate more electrons. This allows elements such as silicon, phosphorus, sulfur, and chlorine to have expanded octets. For example, phosphorus in phosphorus pentachloride has 10 valence electrons after forming single bonds with 5 chlorine atoms. Let's go over the steps of drawing the Lewis structure of a fluorine molecule. First, count all the valence electrons involved in the molecule. You can always refer to the main group number to find out what the valence electron of an element is. Since fluorine is found in the 7th group, it has 7 valence electrons. There are 2 fluorine atoms in this molecule, so there is a total of 14 valence electrons. Next, draw the skeletal structure of the molecule. Don't worry about the lone electrons just yet. Simply draw the single bonds between the atoms involved. Now calculate how many valence electrons are left after drawing the bonds. Since a single bond contains 2 electrons and there is only 1 single bond in this skeletal structure, subtract 2 electrons from 14, which tells us 12 valence electrons are left. Draw these electrons around each fluorine atom as lone electrons or dots. This will be the resulting structure. You can now check if both atoms in this diatomic molecule has fulfilled the octet rule. Since both fluorine atoms have 8 valence electrons around them, this is the correct Lewis structure for molecular fluorine. Let's work on the next example, phosphorus trichloride. First, count all the valence electrons involved in this compound. Phosphorus has 5 valence electrons and chlorine has 7 valence electrons. Since there is only one phosphorus atom and 3 chlorine atoms in this compound, there will be a total of 24 valence electrons in this compound. Let's now determine which element is the central element and which are the terminal atoms. Generally, the least electronegative element is the central atom, except hydrogen, which cannot be the central atom because hydrogen can't form more than one bond. In phosphorus trichloride, phosphorus is the least electronegative element, therefore it is the central atom and the chlorine atoms are the terminal atoms. We can now draw the skeletal structure. You can try to predict how many bonds each element must form to fulfill the octet rule at this point. Since chlorine has 7 valence electrons, it only needs to form one bond to have a total of 8 valence electrons. Phosphorus has 5 valence electrons, thus it is likely to form 3 bonds to have a total of 8 valence electrons around it. Since 3 bonds take up 6 electrons, then we need to subtract that from the total valence electrons, which gives us 18 valence electrons remaining. Place the remaining electrons around the terminal atoms first, then if there are valence electrons left, add them onto the central atom. Since there would still be 2 electrons left after filling the chlorine atom's valence shells with lone pairs, draw those 2 electrons on the central atom, phosphorus. Finally, count the electrons around each atom to make sure that all the elements fulfill the octet rule. Since each element has 8 valence electrons on it now, this is the correct Lewis structure for phosphorus trichloride. Another example we can work on is nitrochloride. First, calculate the total number of valence electrons present in this compound. Nitrogen has 5 valence electrons, oxygen has 6, and chlorine has 7 valence electrons, which gives a total of 18 valence electrons in this compound. Next, identify which element goes in the middle and which are terminal. Since nitrogen is the least electronegative element in this compound compared to oxygen and chlorine, it is the central atom, and oxygen and chlorine are the terminal atoms bonded to nitrogen. Now we can draw the skeletal structure. We can try to predict the number of bonds each element is likely to form as practice. Chlorine is only going to form one bond since it has 7 valence electrons. Nitrogen will probably need to form 3 bonds to fulfill the octet rule since it only has 5 valence electrons. And oxygen needs to form 2 bonds since it only has 6 valence electrons. So we can expect to see multiple bonds in this compound, specifically between nitrogen and oxygen. Before we draw the multiple bonds, however, let's first place the remaining valence electrons as lone electrons around this skeletal structure. Remember to first draw the lone electrons on the terminal atoms, then move on to the central atom if there is still more electrons left. Check if all the elements fulfill the octet rule. Nitrogen only has 6 valence electrons around it, so it does not satisfy the octet rule. This is where we can try to use multiple bonds to ensure that nitrogen has 8 valence electrons. Based on our initial prediction, nitrogen needs 3 bonds and oxygen typically forms 2 bonds to have a total of 8 valence electrons around each of them. Since chlorine already meets our expectation, we can leave it as it is. So let's use one of oxygen's lone pair to form a second bond between nitrogen and oxygen. Remember that we can't simply add an extra pair of electrons into a compound out of nowhere because we already calculated that this compound only has a total of 18 valence electrons. That's why we have to remove a lone pair from oxygen in order to have a second bond between nitrogen and oxygen. Now all of the elements have 8 valence electrons around them, so this is the final Lewis dot structure of nitrochloride. Now I'm going to list the summarized steps of drawing Lewis dot structures. First, add up all the valence electrons of the elements in the compound. Then determine the central element and the terminal atoms according to their electronegativities. Remember that the least electronegative element is the central atom, except for hydrogen. Since hydrogen cannot form more than one bond, it cannot be the central element. Then draw the skeletal structure. At this point, try to predict which atoms form bonds and if single or multiple bonds are needed to fulfill the octet rule. But don't draw the multiple bonds just yet, only draw the single bonds. And notice if there are elements that can have incomplete or expanded octets. Compute and place the remaining valence electrons around the elements as lone pairs of electrons. Remember to place the lone electrons on the terminal atoms first, then move on to the central atom if there are still more electrons remaining. If there are elements that are not fulfilling the octet rule, draw multiple bonds. Here, think back to the predictions you made earlier when drawing the skeletal structure of the compound. Sometimes you may find multiple ways to draw the Lewis structure of a compound. In these cases, you must calculate the formal charge to determine the preferred Lewis structure. Formal charge of an element is equal to valence electron of that element minus the number of bonds it formed minus the lone electrons of that element. Now let's see how to choose the more preferred or the most preferred Lewis structure when we have multiple possible Lewis structures. Lewis structures with more zero formal charges are generally preferred. Negative formal charges should be on the more electronegative atom, and positive formal charges should be on the less electronegative atom. Lewis structures with formal charges closest to zero are more stable, thus preferred. And finally, the further away atoms with opposite formal charges are, the more stable the Lewis structure is, and therefore the more preferred that structure is. Let's look at sulfite ion as an example. There is one sulfur atom in this ion contributing 6 valence electrons. 3 oxygen atoms gives us a total of 18 valence electrons, and there are 2 extra electrons in this ion represented by the -2 charge on the compound. Therefore, there will be a total of 26 valence electrons in this ion. Sulfur is less electronegative than oxygen, so it is the central atom. The skeletal structure of the compound looks like this. Let's predict if there would be multiple bonds in this compound. Oxygen has 6 valence electrons and needs to form 2 bonds to fulfill the octet rule, so we might see some multiple bonds here. Sulfur also has 6 valence electrons, and remember that sulfur is one of the elements that can have an expanded octet. So it can form more than 2 bonds and carry more than 8 valence electrons on it. Now let's calculate the remaining valence electrons. There will be 20 valence electrons left. When we draw those 20 valence electrons on this ion or structure, it will look like this. This structure is one possible Lewis structure for sulfite ion because all the elements have satisfied the octet rule. However, remember that we predicted that oxygen usually likes to form 2 bonds, and sulfur can have an expanded octet. So let's take one lone pair from one of the oxygen atoms and use it to make a second bond with sulfur. This is another way to draw the Lewis structure of sulfite. Let's calculate the formal charge for each structure to determine the preferred one. The formal charge of sulfur on the first Lewis structure that we drew is calculated by subtracting its valence electrons, which is 6, with the number of bonds it's forming, which is 3, and the lone electrons on it, which is 2. This results in a +1 charge on sulfur. The formal charge of oxygen, after calculated the same way, is -1. Since all 3 oxygen atoms have the same number of bonds and lone electrons, The formal charge is the same for all three of them. This structure results in multiple formal charges on the atoms. The formal charge is -2, which corresponds to the ion charge of the compound. Let's calculate the formal charges of the elements in the second lowest structure of sulfite, or the second possible lowest structure of sulfite ion. The formal charge of sulfur is 0. The formal charge of oxygen with the single bond is -1, and the formal charge of oxygen with the double bond is 0. The overall formal charge of this structure is also -2, which makes sense because it is the same as the ion charge of the compound. Comparing the formal charges on this structure to the first structure, this second structure has a greater number of atoms or elements that have a 0 formal charge, which makes it the preferred lowest dot structure. Thank you for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center, and follow us on social media. See you next time.